Picture two people standing in the same place. Not a room, exactly, not a field or a hallway, just a patch of space, as empty as space can possibly be. No air, no dust, no stray light drifting through. Every particle you could name has been swept away until what's left is the emptiest emptiness anyone has ever managed to describe. A perfect vacuum. Nothing now. Both of these people are carrying a small instrument. Think of it as a thermometer, though it's far more delicate than the one in your kitchen drawer. It's built to measure the faintest warmth imaginable. A warmth so slight it's really just the presence or absence of particles, the tiniest whisper of something rather than nothing. The first person stands still, perfectly still. They hold up their thermometer, they read the dial, and it tells them exactly what you'd expect. Nothing, absolute cold. An empty stage with no actors on it. The vacuum is a vacuum, silent and dark and still, and their instrument agrees completely. There is nothing here. The second person does one small thing differently. They begin to accelerate, not to move, moving steadily wouldn't matter, but to speed up, to push harder and harder through that very same patch of perfect emptiness. And as they do, something impossible happens. Their thermometer, held in the identical nothing, begins to register a warmth. A faint one, a soft hiss of particles where the other person swore there were none. Their instrument fills, very gently, with the signal of a bath of warmth, as though the empty space around them were not empty at all, but a room heated by some invisible fire. Here's the part that should keep you up at night, except that I very much hope it won't. Neither of them is wrong. Welcome to the Curious Voyager. It's lovely to have you here tonight. Wherever you are, a bed with the blanket pulled up to your chin, a couch with one lamp still glowing in the corner, a train carrying you quietly through the dark, I'm glad you found your way to this little pocket of calm. Settle in. Let your shoulders drop away from your ears. Let the phone rest somewhere it won't need holding. And before we drift any deeper, tell me, where in the world are you listening from tonight? What time is it in your corner of the dark? I always love to imagine the map of us, all these quiet windows lit up in different countries, all of us following the same slow thread towards sleep. Leave a little note if you feel like it. It's a gentle thing, reading in the morning where everyone was resting. If you enjoy these slow journeys and you'd like more of them, a like and a subscribe genuinely helps this sleepy little channel keep going. I know it's a small thing to ask, and I ask it softly. Small creators like me really do rely on your support. One tap in the dark, and it helps more than you'd think. And to those of you already subscribed, already returning night after night, thank you. Truly, you're the reason there's a next journey at all. Now, a promise, before we begin, because I think promises help you rest. This is going to be slow, slower than you might be used to. We are going to take one strange, beautiful idea and turn it over in our hands for a long, long while, gently, from every side, and we are in no hurry whatsoever to reach the end. There's no exam at the end of this. There's no moment where I'll ask you to have kept up. If your eyes close before I finish, and I rather hope they do, that's not a failure. That's the whole point. The ideas will still be here. They'll wait for you. You can always come back and find them exactly where you left them, patient in the dark. So please, don't try to hold on to every word. Don't grip. Some of what I say tonight will slip past you into sleep, and some of it will settle somewhere quiet, and both of those are perfectly fine. I'll say the strange things more than once, in more than one way, precisely so you don't have to catch them the first time. You can let the sound of it carry you the way a current carries a leaf. No effort, no paddling, just drift. And I'll try, as I always do, not to make this so interesting that it keeps you awake. Though I'll admit, right at the start, that tonight's idea is a genuinely strange one, so if it does keep you up a little, well, at least you'll have learned something lovely about the shape of reality. A fair trade, I think. A fair trade. Because here's what we're going to sit with tonight. That story I told you of the two people and the one patch of empty space, the still one who measures cold nothing, and the accelerating one whose instrument fills with a warm hiss of particles, both of them right. That isn't a riddle I made up. It isn't a metaphor or a poem or a bit of clever wordplay dressed up as physics. It is, as far as our very best understanding of the universe can tell, a real prediction. It has a name. It's called the Unruh effect, and sometimes, to honour the three people who found it, the Fulling, Davies, Unruh effect. We'll meet all three of them before the night is through, slowly, the way you meet people at a quiet dinner, one at a time. And the claim at the heart of it is this. If you accelerate hard enough through what everyone agrees is a perfect vacuum, a true and total nothing, then a thermometer you carry with you should read a temperature above absolute zero. The void, to you and you alone, should feel faintly warm, as though empty space were a kind of warm bath, and speeding up were the same as lowering yourself into it. I know how that sounds. I know it sounds like the sort of thing someone says to seem clever and then never quite explains, and you go away feeling you've been handed a puzzle box with nothing inside. And I think, if you've spent any time at all with the strange corners of physics, you've had that feeling before. You've heard 100 times that empty space isn't really empty, that the vacuum is secretly full of something. Everyone says it. It's become almost a slogan. And then, so often, they stop right there, at the edge of the interesting part, and leave you standing at the cliff without ever telling you what's at the bottom. Tonight, we're going to climb down. Slowly, all the way to the bottom of that thought, to the strangest and most honest place it leads. And I'm going to be careful with you the whole way. Careful, in particular, to always tell you the difference between what physicists are quite sure of and what they merely suspect, between what has been measured and what has only been predicted. Because that honesty is, I think, the most soothing thing of all. There's a real peace in someone telling you plainly, this part we know, and this part we don't. So let's begin there, shall we? Let's begin with the ground beneath the whole idea. Let's begin with the emptiness itself, and ask what it really is. When you and I say the word empty, we usually mean something quite simple. A cup is empty when there's no tea in it. A room is empty when everyone's gone home. Empty means the stuff was here, and now it's not. And so, naturally, when we imagine truly empty space, the vacuum between the stars, the vacuum a scientist builds in a sealed chamber by pumping every last particle away, we picture the same thing, only more so. We picture a stage with the actors gone, the props cleared, the lights off, an empty stage, pure nothing. A black, silent, motionless absence, waiting for something to happen. That picture is wrong. And it's wrong in a way that took some of the finest minds of the last century a very long time to understand, so please don't feel you should have known. The truth is gentler and far stranger than that. To see it, we have to change just slightly what we think the universe is made of. In our ordinary way of thinking, the universe is made of particles, little grains of matter, electrons and photons and the rest, scattered through an empty container of space. Take the grains away, and you're left with the empty container. But the modern picture, the one physicists have been building and testing for the better part of 100 years, says something different. It says the fundamental things are not the grains. The fundamental things are fields. And a field is simply something that has a value at every point in space, everywhere, all at once, filling everything. You already know one field, even if you've never called it that. The magnetic field around a magnet, the invisible influence that tugs a compass needle or grabs a paperclip through the air, that's a field. It's not a thing sitting in one place. It's a condition spread through all the space around the magnet, present everywhere, stronger here, weaker there, but never truly absent. Now, the deep idea is that everything is like this. There's a field for electrons that fills all of space, a field for light that fills all of space, a field for every kind of particle you've ever heard of, each one spread through the whole universe like an invisible, endless ocean. And a particle, an electron, a photon, a single grain of light, is not really a separate object at all. It's a ripple in its field, a little wave, a disturbance travelling across that endless ocean, the way a wave travels across the sea while the sea itself stays where it is. Hold on to that image for a moment, because it's a soft one and it will carry us a long way. The sea, everywhere, and the waves, coming and going upon it. So now ask the question again. What is empty space? It's not the absence of the ocean. The ocean is always there, the fields fill everything, and you can't pump them out of a chamber the way you pump out air, because they aren't in the chamber, they are the fabric the chamber is made of. Empty space is simply the ocean when it's as calm as it can possibly be. No waves, no ripples, the lowest, quietest, most settled state the fields can be in. Physicists have a name for this calmest possible condition. They call it the ground state. And the ground state of all the fields together, the flattest the ocean can lie, that is what we mean, really, by the vacuum. The quantum vacuum. But here's the first turn in the path, the first place where the ordinary picture breaks and something lovelier appears. That ocean can never be perfectly, absolutely still. It can't. There's a rule woven into the deepest level of physics that forbids it. The fields are always trembling, just slightly, even in their calmest state. Even at the very bottom, even in the ground state, there remains a faint, irreducible shiver, a restlessness that can never be smoothed away. Physicists call it zero-point motion, or zero-point fluctuation, and the name is rather beautiful when you unfold it. 0 point, because it's the trembling that's still there even at the zero. Even when you've taken away every last bit of heat and energy you possibly can, and the fields have nothing left to jitter with, they jitter anyway. It's the motion that has no cause you can remove, the shiver at the bottom of everything. So the true picture of empty space is not a dark, dead, motionless stage. It's an ocean, stretched everywhere, lying as flat as the laws of nature will allow, which is to say, still faintly, endlessly, quietly trembling. Calm, but alive. Silent, but not asleep. That is the nothing we're talking about tonight. That is the emptiness that, to someone accelerating through it, might just begin to feel warm. Now, I want to be very careful here, because this is exactly the point where a great many tellings of this story go astray, and I promised you I'd be honest. You'll often hear people describe that trembling of the vacuum by saying it's full of particles, little particles constantly popping into existence and vanishing again, appearing and disappearing too fast to catch. Virtual particles, they're called, flickering in and out of the emptiness like sparks over a fire. It's a vivid image, and it's not exactly wrong, but it's a picture that's been repeated so many times, so loosely, that it's become almost meaningless. It's the slogan I mentioned, the thing everyone says, and no one finishes. And I don't want to lean on it tonight, because I don't think it's the clearest way to see what's really happening. The clearer way, the gentler way, is the one we've already built. Fields, everywhere, a ground state that still shivers. That's all. That's the whole foundation. Not a swarm of tiny things buzzing in the dark, but a smooth, endless medium that can never hold quite perfectly still. Keep the ocean. Let the sparks go. But now I imagine you might be feeling a very reasonable doubt, the kind that keeps a curious mind from settling. It's all very well, you might think, to tell a nice story about trembling fields and calm oceans. But how could anyone possibly know? If this vacuum is invisible, if its trembling is the faintest thing in all of physics, if you can't pump it out or hold it in a jar, then isn't this just a pretty story? Isn't it just words? How could anyone ever have touched the untouchable and shown that empty space is really this restless, shivering thing rather than plain and simple nothing? It's a fair doubt. It's the right doubt. And the beautiful thing is that it has an answer, a real one, measured in a real laboratory, with real instruments more than once. The vacuum's shiver has been felt, and the story of how is one of the loveliest small stories in all of physics, so let me tell it slowly, because it's the thing that turns tonight's whole idea from a fairy tale into something you can trust. It begins in 1948 with a Dutch physicist named Hendrik Casimir. Casimir was thinking about this restless vacuum, this ocean of trembling fields, and he asked himself a very simple, very physical question. What would happen if you took two ordinary metal plates, flat, uncharged, no batteries, no magnets, nothing special about them at all, and held them extremely close together, facing each other in a perfect vacuum? Not touching, just very near, a hair's breadth apart. What would the trembling emptiness between them do? His answer, when he worked it through, was astonishing in its quietness. He predicted that the two plates would be pushed together. Gently, but really, a genuine force, drawing them toward each other out of nothing but the vacuum itself. Let me try to give you a feeling for why, because the picture is a soft and satisfying one. Remember the ocean, the trembling fields filling all of space. That trembling happens at every scale, long, slow waves and short, quick ripples. All of them, all at once, everywhere, now slide two plates very close together, facing each other. In the narrow gap between them, there simply isn't room for the longest, slowest waves. They don't fit. Like a jump rope tied between two posts that are too close together. Only certain wavelengths can exist in the space you've allowed. So the trembling in the gap becomes a little quieter, a little thinner than the full, unrestricted trembling in the wide open space outside the plates. And that difference, a little less shiver inside than outside, means the vacuum outside is pressing a touch harder than the vacuum inside. The two plates get squeezed together by the very emptiness around them, not by magnetism, not by static, by nothing, by the difference in how the nothing trembles on either side of them. That gentle press has a name now. We call it the Casimir effect, and the force it describes is a real physical pressure exerted by empty space upon two plates that have no business feeling any force at all. For a long while, Casimir's prediction was just that, a prediction. A beautiful piece of reasoning, sitting in a journal, waiting, The force he described is fantastically small, you see. It only becomes noticeable when the plates are almost impossibly close, closer than the width of a speck of dust, and measuring a push that faint. Between two surfaces, held that near without letting them crash together, was beyond what anyone could do for decades. So the idea waited. It waited the way tonight's ideas will wait for you if you drift off, patiently, in no hurry. And then, at last, the measurements came. In 1997, nearly 50 years after Casimir first imagined it, a physicist named Steve Lamoureux managed to measure that ghostly force directly and found it agreed with the prediction. And soon after, in 1998, another physicist, Umar Mohideen, measured it again with even finer precision, pushing the confirmation tighter still. The vacuum, it turned out, really does push. The trembling is real. The ocean is really there, and it really shivers, and its shiver leaves a fingerprint you can catch with patient enough hands. I want you to sit with what that means, softly, because it's the ground we'll be standing on for the rest of the night. It means the emptiness we've been describing is not a metaphor. It's not a manner of speaking, not a poet's flourish. Empty space is a physical thing with a physical state that can push on physical objects and be measured doing so. The nothing has been touched. It left a mark on a real instrument in a real laboratory twice over, decades after it was foreseen. And this is the quiet thread I want to hand you now, to carry with you into sleep. It is this very same vacuum, this exact same restless, trembling, measurably real emptiness that would begin to feel warm to someone accelerating through it. Not a different, more exotic nothing. Not some special vacuum cooked up for the occasion. The same one. The Casimir vacuum, the one whose gentle push we've caught in the laboratory, is the Unruh vacuum, the one that hides a faint warmth from anyone moving through it fast enough. One emptiness, two faces. We've seen the first face already, felt its push between two plates. Tonight, slowly, we're going to turn it around and look at the second. So let's take a breath here. Let's not rush on. You've come a long way already, and none of it needs holding tightly. Let me just lay the pieces down beside you one more time, gently, so they're there in the quiet, whether you're still awake to hear them or already halfway into a dream. Empty space is not empty. But not for the reason everyone repeats. It's not a swarm of flickering sparks. It's an ocean, fields, everywhere, filling all of space, the true fabric of the world. And that ocean, even in its calmest state, even in the deep silence we call the vacuum, can never hold perfectly still. It shivers, a faint, endless, uncaused trembling, the zero-point motion, the restlessness at the very bottom of things. And we know it's real, not because someone told us a nice story, but because Hendrik Casimir predicted in 1948 that this trembling would press two nearby plates together, and because Steve Lamoureux in 1997 and Umar Mohideen in 1998 went into their laboratories and felt that press with their own instruments and found it just where it was foretold. That's the stage set. That's the emptiness we're working with. Real, measured, trembling, and, as far as anyone can tell, utterly the same no matter who's looking at it. Except that's the thing we're going to spend the rest of tonight gently unraveling. Because for all that the vacuum is real and solid and measurable, the strangest question of all turns out not to have a fixed answer. And the question is this simple, this childlike. How many particles are in this patch of space? You'd think, surely, that this is the most straightforward question you could ask. Count them. However many there are, and everyone who looks should agree, the way everyone agrees how many chairs are in a room or how many stars in a photograph. The number of things in a place is a fact about the place. Isn't it? Surely it's a fact about the place. And yet, come back to the two people we started with, standing in that one patch of perfect vacuum. The still one whose thermometer reads nothing, empty, absolute cold, and the accelerating one whose identical thermometer in the identical space begins to fill with the warm hiss of particles. They are asking the same question, how many particles are here, of the same emptiness, and they are getting different answers. And, as I told you at the very start, and as I'll keep telling you because it's the heart of the whole thing, neither of them is making a mistake. Neither instrument is broken. Neither person is confused. They simply, honestly disagree. How can that be? How can the number of particles in a place depend on how you're moving through it? How can speeding up conjure warmth out of a cold and settled nothing? That's the mystery. That's the whole gentle mystery we've come here to sit inside tonight. And I'm not going to answer it all at once, because there's no rush, and because the answer is worth savouring slowly, in pieces, the way you'd unwrap something delicate. But I'll give you the shape of where we're going, so you have a soft thread to follow even as you drift. The secret, when we finally reach it, will turn out to live in the word particle itself, in what a particle even is, down at the bottom, in the language of those trembling fields. We've been speaking, you and I, as though a particle were an obvious thing, a ripple on the ocean, plain to see. But it turns out that deciding whether a ripple is really there, whether the ocean is truly flat or secretly full of waves, is not as simple as looking. It depends, in a way we'll unfold very gently, on something about the observer, on their clock, on how their sense of time is threaded through the trembling. And two people moving differently through the same space carry, in a real and precise sense, two different clocks. And so they slice the same ocean into waves in two different ways, and honestly count two different numbers. That's where we're headed. Toward the strange and beautiful idea that the number of particles in a room might not be a fact about the room at all, but a fact about you, about how you move, about the path you carve through the emptiness. Toward the idea that empty might not be a property of space, but a relationship between space and the traveller passing through it. We're not there yet. We've only laid the foundation, the real, trembling, Casimir-tested vacuum, the same one on both sides of the story. That's plenty for now. That's a good, solid thing to rest on. So let yourself rest on it. Let the two people stand there in the dark of that perfect vacuum, one still, one speeding up, both holding their little thermometers, both perfectly, honestly right. Let the question hang softly in the air. How can the emptiness be warm to one and cold to the other without needing, tonight, to force it closed? We'll open it, slowly, together, in a little while. There's time, there's all the time in the world. For now, just breathe. Feel the weight of you against whatever's holding you, the mattress, the cushion, the seat. Notice how the room around you, the air you can't see, the space between you and the ceiling, is that same trembling ocean we've been describing, filling everything, quietly alive, pressing ever so faintly on everything it touches. You are lying right now in the very vacuum we've been talking about, dressed in air, wrapped in fields, held in the endless calm shiver of the ground state of the world. There's something rather comforting in that, I think, that even the emptiest emptiness is never truly cold and dead, that the nothing is, in its own faint way, always gently trembling, always quietly there, and somewhere in that same nothing, if only you could push against it hard enough, fast enough, harder and faster than anything you or I or any machine we've ever built could manage, that quiet trembling would rise, just a touch, into something a thermometer could feel, a warmth in the void, a fire with no fuel, the empty room glowing faintly for you and no one else, simply because of how you moved. We'll get to all of it. Slowly, how much warmth, and why so little, and why that little is exactly why no one has ever caught it. Who first dreamed it up, and how they stumbled into it while trying to understand something else entirely. Something to do with black holes, of all things, those great dark drains in the fabric of space. And the honest, careful truth about what we've measured and what we've only ever predicted, because that truth is the whole reason you came, and I mean to keep it lit for you the whole way through. But not tonight. Not all at once. Tonight we've done the gentlest and most important thing. We've learned what the emptiness really is. We've learned that it's real, and trembling, and touchable, and the same on both sides of our little mystery. And we've let the mystery itself settle softly into the room beside us, in no hurry to be solved. So stay with me if you're still here. And if you're already drifting, that's just as good, better, even. The two travellers will keep their patch of vacuum. The ocean will keep its shiver. And the strange warm question of how empty space could ever feel warm will wait, exactly where we left it, patient and quiet, until we're ready to pick it up again. So, let's begin where we left off. Two travellers. One patch of perfect vacuum. Two different readings on their instruments, and the question hanging between them like something you can almost touch. How? How can two honest observers, both careful, both using instruments that work, look at the exact same region of space and come away with different answers about what's there? It sounds at first like a contradiction, like a mistake somewhere in the setup. And if you've drifted just a little, don't worry. That feeling, that mild unease, that sense of there being a puzzle you can't quite put your hands on, is exactly right. It means you're following it. We're going to follow it now, together, step by slow step. And I want to reassure you before we go any further, the answer is not a trick. It isn't a failure of measurement, or bad calibration, or some sleight of hand in the mathematics. Both observers are correct. And once you understand why, not just that it's true, but why, in plain language, the explanation without the jargon, although we'll meet a few technical words, and we'll unwrap each one as it comes. Once you understand why, you'll have arrived somewhere genuinely strange and genuinely wonderful. Not because it tells you something mystical, but because it tells you something precise and honest about the nature of what we mean when we say a particle exists. That's where we're going tonight. We're going slowly. And if you close your eyes at some point during the journey, I'll still be here when you come back, or when you wake, and the idea will still be sitting quietly where we left it. Let's talk about what a particle actually is. This is, in a way, the whole secret, and it's a secret that's embarrassingly well hidden in plain sight, because in everyday life a particle seems obvious. A particle is a thing, a small thing, an electron, a photon, a little discrete chunk of something. You shoot it from a gun, it hits a screen, you call it a particle. Simple, but in quantum field theory, the framework physicists use, when they need to talk about both quantum mechanics and special relativity at the same time, the definition of a particle turns out to be far stranger than that. It turns out to depend on something you might never have expected it to depend on. It depends on your notion of time. Here is why. Imagine a quantum field, one of those great invisible fabrics that fills all of space, like the electromagnetic field that carries light, or the fields that carry electrons and quarks. At every point in space, and at every moment in time, this field has a value. And those values ripple. They oscillate. The whole field, everywhere, is vibrating in patterns, the way the surface of a deep lake vibrates when you've disturbed it, each ripple a superposition of countless smaller waves, each wave a mode of the field, a particular frequency, a particular shape. Now, in quantum mechanics, energy comes in packets, so each of these modes, each ripple pattern of the field, also has its energy divided into discrete steps. The lowest step is the ground state, no ripple, or really the quietest the field can be, which we've already learned is not quite quiet, because 0-point fluctuations are always there. But the next step up, the first excited state of a particular mode, is what physicists call having one particle in that mode. A particle, in this picture, is not a small lump of stuff sitting in space. A particle is an excitation of a field. It's a ripple that has been promoted from the ground state to the next level up. And here is the delicate and important thing. To talk about excitations above a ground state, you have to know which state is the ground. You have to know what lowest energy means. And in quantum field theory, to define which modes of the field carry positive energy and which carry negative energy, you need a way to measure energy. You need a clock. Because energy and time are deeply tied together in physics, one of the most fundamental relationships there is, going all the way back to the Hamiltonian formalism, the mathematics that governs how systems evolve. And the rate at which a mode oscillates, which determines whether it counts as positive or negative frequency, is a rate with respect to some notion of time. For an inertial observer, someone sitting still or moving at a constant speed, not accelerating, the natural clock is what physicists call Minkowski time. Flat, ordinary. The time that comes with the flat spacetime of special relativity, named for Hermann Minkowski, the mathematician who first gave Einstein's special relativity its elegant geometric form. In Minkowski time, the modes of the quantum field divide cleanly into positive frequency modes and negative frequency modes. The positive ones carry positive energy, the negative ones carry negative energy. And the rule, the boundary condition that says what the vacuum state is that the vacuum has no positive frequency excitations. Nothing sits in any of those upward steps. The field is as quiet as it can be, given the trembling it can never quite escape. This is the Minkowski vacuum. The vacuum of the inertial observer. Absolute cold, in the sense that there's nothing there to have a temperature. No particles, just the irreducible shiver of 0-point fluctuations, going nowhere, doing nothing, unable to be removed. Now, start moving. Not just moving, accelerating, pushing, constantly, harder and harder, so that you're not drifting at a steady rate through space, but actually changing your speed. You've left the inertial frame. And here is where time changes on you. An accelerating observer doesn't experience Minkowski time. The clock they carry, ticking at their wrist or in their instruments, runs differently. Not just slower in the ordinary relativistic sense, differently in a deeper way. Their time, their natural coordinates for measuring where they are and when they are, follow a different geometry. This geometry has a name, and we'll use it because it's the name of the man who first worked it out. Walther Rindler, a physicist who spent decades at New York University, developed these coordinates in the 1950s and 1960s. And in Rindler coordinates, the accelerating observer's natural description of the same spacetime is genuinely different. Not wrong, different. Different in the way that a map drawn from the North Pole is different from a map drawn from the equator. They describe the same Earth. They don't look the same, and because the coordinates are different, the notion of what counts as positive frequency and what counts as negative frequency is different too. The accelerating observer, working in Rindler time, carves up the modes of the quantum field in a different way from the inertial observer, working in Minkowski time. Now, both of them are looking at the same field. The same field is vibrating across the same space, but one observer organizes those vibrations one way and the other organizes them another way. And when you translate between the two, when you take the Minkowski vacuum, the quiet, inertial ground state, and you rewrite it using the accelerating observer's mode, decomposition, something remarkable falls out of the mathematics. The translation is done by a procedure called the Bogolyubov transformation, named for the Soviet physicist Nikolai Bogolyubov, who developed it in the 1940s in a different context entirely, the theory of superfluids, of liquids that flow without friction, but whose mathematical machinery turns out to be exactly what's needed here. The Bogolyubov transformation is, at its heart, a way of relating one set of building blocks to another. Think of it like this. If you have a collection of Lego bricks and someone else has a collection of differently shaped bricks, and both collections are supposed to build the same house, then you can write a recipe that says, my 2-stud brick and my 4-stud brick together make up what you're calling your L-shaped piece. That recipe, the set of coefficients that translate one builder's vocabulary into the other's, is the Bogolyubov transformation. When physicists apply it here, when they translate the Minkowski vacuum into the Rindler language of the accelerating observer, those transformation coefficients are not zero. They're not nothing. They mix the creation operators and the annihilation operators, the mathematical tools that add or remove excitations from the field. And when you mix them, something that looks like nothing in the Minkowski language looks, in the Rindler language, like a specific, warm, busy collection of excitations. A thermal distribution, specifically a Bose-Einstein distribution. The kind of distribution that describes how energy gets shared among the modes of a quantum gas at some particular temperature. The Rindler observer's mode decomposition, applied to the Minkowski vacuum, reveals a vacuum that is full of excitations, full in precisely the same mathematical sense as a gas at a finite temperature. That temperature is the Unruh temperature. It is a direct consequence of how the two mode decompositions relate to each other. And the Bogolyubov coefficients carry exactly the right factors to make it thermal, not approximately thermal, not roughly thermal, but thermal in the precise, rigorous sense, satisfying the KM's condition, which is the gold standard mathematical criterion physicists use to test whether something is genuinely in thermal equilibrium. KM stands for Kubo, Martin, Schwinger, three physicists who independently identified the mathematical fingerprint of a true thermal state. The accelerating observer's vacuum isn't just warm in some hand-wavy sense, it satisfies the strictest mathematical definition of warmth. But we've jumped a little ahead of ourselves. Let me bring this back to something you can hold. Here is the plain language version of everything we just said. A particle is a ripple in a field that has been raised above its ground state. But what ground means, what the lowest energy state looks like, depends on how you're measuring energy. And measuring energy requires a clock. And a clock that belongs to someone standing still, and a clock that belongs to someone accelerating, run through time differently. So when the standing still observer looks at the field and says, "I see no excitations, I'm in the ground state, there are no particles here," they are correct from their point of view, using their clock. And when the accelerating observer looks at the very same field and says, "I see excitations everywhere, I'm immersed in a thermal bath, there are particles here," they are also correct, from their point of view, using their clock. Neither is measuring wrongly, they are measuring the same mathematical object, the quantum field, but projecting it onto different coordinate systems. The way you might project the light from the same projector onto two differently angled screens and get two different pictures. The picture that lands on your wall isn't wrong, and neither is the picture on mine. They're different views of the same light. That's the Unruh effect. Not a metaphor for it. Not an analogy of it. That is, in the clearest plain language I can manage, what it is. And now I want to introduce you to something beautiful. A thought experiment so clean and so precise that physicists use it as the gold standard way of thinking about this. It comes from Bryce DeWitt. Bryce Seligman DeWitt was an American physicist, one of the great figures of 20th century quantum gravity, who worked for decades at the University of Texas at Austin. He was the kind of physicist who liked to take an abstract idea and reduce it to the simplest possible physical system that still captured the essence of the problem. And in the 1970s, when the Unruh effect was being worked out, he asked a beautifully minimal question. What is the simplest possible thing you could call a particle detector? And the answer he came up with is this: a two-level system. Something with exactly two states, a low-energy ground state and a high-energy excited state, coupled to the quantum field. Like a very simple atom or a small switch that can be either off or on. If the quantum field has particles in it, they can be absorbed, and the switch goes from off to on. If the field is in its ground state, nothing happens, and the switch stays off. This is the Unruh DeWitt detector. A completely idealized, completely minimal particle detector. No batteries, no screen, no complicated electronics. Just a small system with two energy levels dragged through space-time and then checked afterward to see whether it got excited. And what does the Unruh DeWitt detector say? If you carry it along an inertial path, straight, at constant speed, no acceleration, and you start it in its ground state, it stays there. The Minkowski vacuum offers it nothing. It doesn't click, no particles absorbed, everything quiet. But if you drag that same detector along an accelerating path, if you push it steadily, so that it follows a trajectory of constant proper acceleration through flat, empty space, it gets excited. It clicks. Not randomly, not sometimes and sometimes not. It gets excited at a rate that follows a precise thermal distribution, exactly as if it were sitting in a warm gas at a temperature that depends on the acceleration. The Unruh temperature. This is important. The Unruh DeWitt detector doesn't have opinions about coordinates. It doesn't know about Minkowski versus Rindler. It is a tiny physical system following a path, coupled to a field, and you check it afterward to see what happened. And what happens is, it behaves, measurably, as though it were immersed in a warm thermal bath when it accelerates, and as though it were in a cold, empty vacuum when it doesn't. The mathematics of the coordinate transformation, which might feel abstract when we talk about it in terms of mode decompositions and Bogolyubov coefficients, shows up as a real physical consequence for a real physical object dragged along a real physical path. There is something almost tender about it. This tiny idealized thermometer, just two states, the simplest possible thing that could count as a detector, dragged hard enough through empty space, clicking quietly into its excited state, as though the void itself were reaching up and tapping it on the shoulder. But there is something even deeper here, something I promised you and haven't yet delivered, because I wanted the idea to have time to settle. And now it's ready. When you accelerate, you don't just change your relationship to the field's modes, you change your relationship to space-time itself. Specifically, and this is one of the most remarkable geometrical facts that comes out of Rindler's analysis, a uniformly accelerating observer has a horizon. Let that sit for a moment. An event horizon is something we usually associate with black holes. A black hole's gravity is so intense that beyond a certain radius, the event horizon, nothing can escape, not even light. What happens inside the horizon is, in the most rigorous sense, causally cut off from what happens outside. An observer outside a black hole can never receive any signal from beyond the horizon. It's not that the signals are too faint or too slow, they simply cannot arrive. The geometry of space-time doesn't permit them. Now imagine you're accelerating, not falling into a black hole, just accelerating through perfectly flat, empty space with no mass anywhere nearby. You're being pushed. Constantly. And imagine that very far behind you, impossibly far behind you. Someone fires a light signal in your direction, trying to catch you. If your acceleration is constant and you're moving through flat space, then there exists a boundary, a surface in space-time, from beyond which no light signal can ever reach you, no matter how long you wait. The reason is geometric. You're always accelerating away. And there are events so far in the past or so deep in the region behind you that any light emitted there can never make up the distance, because you're always gaining ground, always pulling away. The surface beyond which signals can never reach you is the Rindler horizon. Not a surface in space exactly, a surface in space-time, a slice through the geometry of your situation, but a genuine, mathematically rigorous causal horizon, an event horizon, created not by mass, not by gravity, but purely by motion, by the fact of your acceleration. And behind it, in the region of space-time that is forever hidden from you, the region whose signals will never arrive at your instruments, physicists call the Rindler wedge. Your wedge, the region you can access, is the half of space-time your acceleration keeps you inside. The other half is cut off, and there is an infinite amount of space-time in that cut-off region. Events, fields, everything that might be happening on the other side of your horizon, you will never know about any of it, for as long as you keep accelerating. This is not a trivial thing. It is deeply connected to why the accelerating observer sees a thermal bath. The Rindler horizon is the flat space twin of a black hole event horizon. And the thermal radiation the accelerating observer detects is, in a precise mathematical sense, the same phenomenon as the radiation a black hole emits, which we will come to, and will take our time with it, because the connection between these two things is one of the most beautiful and unexpected bridges in all of theoretical physics. But for now, the Rindler horizon does something specific and important for our story. It explains, geometrically, where the warmth comes from. Think of it this way. The quantum field exists everywhere. Its modes, its ripple patterns, extend across all of spacetime. But the accelerating observer can only access the field modes in their own wedge, the part of spacetime on their side of the horizon. The modes that extend into the hidden region beyond the Unruh horizon are simply not available to them. They cannot receive signals from there. They cannot measure those modes. And what happens in quantum physics when you can only access part of a system and not the rest? When you're forced to ignore half of the quantum state? The answer is a beautiful and slightly melancholy one. When a quantum system is in a pure state, a perfectly well-defined, zero-entropy state, completely known, and you take that system and divide it in two, and you can only look at half of it, what you see is not a pure state. You see a mixed state, a state with entropy, a state that looks, for all your measurement purposes, exactly like a thermal state at some temperature. This is the mathematics of entanglement and partial traces, and it is not unique to quantum gravity. It's a completely general feature of quantum mechanics. Whenever two parts of a quantum system are entangled with each other, and you can only look at one part, the piece you see looks warm. The Minkowski vacuum, the global quantum vacuum seen by the inertial observer, is an entangled state. Its modes on both sides of the Unruh horizon are entangled with each other in the same way that two particles in a perfectly correlated quantum state are entangled. The inertial observer can see all the modes, both sides of the horizon, and the whole state looks like a pure zero-entropy vacuum to them. Nothing there. But the accelerating observer can only see one side. Their horizon hides the other half. And when you trace over the hidden modes, when you do the mathematical operation of saying, I have to treat the modes I can't see as unknown, I'll average over them, what's left is exactly a thermal density matrix. A state that looks, by every measure the accelerating observer can make, exactly like a warm gas at the Unruh temperature. The warmth the accelerating observer feels is the warmth of not knowing, or rather, of being unable to know. The horizon keeps half the vacuum's correlations hidden, and the visible half, missing its partner, becomes warm. This is perhaps the deepest way to understand why the two observers disagree. The inertial observer has access to all the information. They see the whole entangled state, pure and cold. The accelerating observer is blocked from half of it by a horizon they themselves have brought into being through their own motion. And that missing half warms everything they can see. I find this extraordinarily beautiful, and I hope you do too. There's something almost poignant about it. The accelerating observer's warmth is, in a sense, the warmth of separation, the warmth of a horizon you can't cross. The quantum vacuum, felt as a whole, is utterly cold, but cut off from half of it as acceleration does to you, and the half you have left glows. Now, we've been talking about what the accelerating observer sees, and we've unpacked three different ways of arriving at the same answer. First, the mode decomposition argument, their notion of time carves the field differently, and the Bogolyubov transformation relating the two descriptions produces a thermal bath. Second, the detector argument, a simple two-level Unruh, DeWitt detector, dragged along an accelerating path, genuinely gets excited as though immersed in a warm gas. Third, the entanglement argument, the Unruh horizon hides half the vacuum's quantum correlations, and the visible half, deprived of its partner, becomes warm. Three roads, same destination, and this convergence, this fact that you can arrive at the Unruh temperature from very different mathematical starting points and always get the same answer, is one of the reasons physicists take it seriously, even without a direct experimental confirmation. But we're getting ahead of ourselves again. We'll talk about what's been measured and what hasn't, about the honest state of the evidence, in our own good time. For now, let's let the three roads sit beside each other and appreciate the company they keep. Let me come back to something I said a little while ago, because I want to look at it more carefully. I said that the accelerating observer has a horizon, and that this horizon is the flat space twin of a black hole event horizon. And I said rather quickly that the thermal radiation the accelerating observer sees is, in a precise sense, the same phenomenon as what Stephen Hawking predicted for black holes. That connection is real and deep, but it deserves more than a glancing mention. Let me show you one more angle on it before we rest here tonight. The Rindler horizon is a horizon made of motion. Not of mass, not of gravity, not of anything physical standing in the way. Just acceleration, consistently applied, curving the geometry of what you can and can't receive. It is, mathematically, an event horizon like any other. And wherever there is an event horizon, the quantum vacuum does something particular. It produces radiation. The modes of the quantum field that straddle the horizon, some modes that have part of their wave pattern on your side and part on the other side, are disturbed by the fact of the horizon. They can't simply pass through unaffected. The horizon breaks the field's natural symmetry, and that breaking has consequences. One consequence is the entanglement we described. Another consequence, calculable from a slightly different angle, is that an accelerating observer will see a thermal flux of particles coming from the direction of the horizon, the way a warm object radiates heat. This is the Unruh radiation. Not particles falling on the observer from outside, particles appearing, in a sense, at the horizon, radiating outward from it. Just as Hawking radiation appears at the horizon of a black hole and radiates outward into the universe. And for an observer hovering just outside a black hole, not falling in, but hovering, fighting gravity to stay in place, that hovering is itself a form of acceleration. You have to fire your rockets constantly to stay fixed at a certain distance from the black hole, because gravity is always pulling you in. To remain stationary above the horizon, you must accelerate constantly, and that acceleration has a Unruh temperature. And that Unruh temperature, carefully accounting for the gravitational redshift that changes the energy of photons as they travel away from the black hole, turns out to be exactly the Hawking temperature that Hawking derived from a completely different calculation. Two calculations, two different methods, the same number. That agreement is not a coincidence. It tells us something true about the deep structure of the connection between acceleration and gravity, which brings us, finally, to the most elegant single sentence in this entire story. Einstein's equivalence principle. It's a principle that goes back to one of Einstein's famous thought experiments, developed in the years between 1907 and the completion of general relativity in 1915. The principle says this: if you are inside a small sealed box, you cannot tell the difference between being stationary in a gravitational field and being accelerated by a rocket. A ball dropped inside the box falls the same way whether you're sitting on the surface of the Earth or being pushed through empty space at 1 g of acceleration. The physics is the same. The two situations are locally indistinguishable. This principle is one of the cornerstones of general relativity. Einstein called it the happiest thought of his life. And it connects the Unruh effect and the Hawking effect with a directness that once you see it, you can't unsee. If acceleration and gravity are locally equivalent, and if acceleration produces a thermal bath at the Unruh temperature, then gravity, the presence of a massive object that forces observers to accelerate in order to stay stationary, must also produce a thermal bath. And it does. That's Hawking radiation. It is the gravitational version of the Unruh effect. Two views of the same underlying vacuum physics, one seen in flat space by an accelerating observer, one seen in curved space by an observer hovering above a horizon that gravity has carved out of spacetime. The equivalence principle is the bridge between the two. It is what makes the Unruh effect so important, not just as a curiosity about accelerating observers, but as the flat space foundation of one of the most profound predictions in all of modern physics, Hawking's discovery that black holes are not truly black, that they radiate, that they have a temperature, and that they therefore eventually, over unimaginable spans of time, evaporate. And all of this came from thinking about particles, from asking what it really means to say that a particle is there. There is, I think, something quietly extraordinary about the path that led here. William Unruh was not initially trying to find out whether accelerating through empty space would feel warm. He was trying to understand Stephen Hawking's 1974 prediction about black holes. Hawking had shown, using a mixture of quantum field theory and general relativity that was new and not fully worked out, that black holes must radiate. Unruh, along with Paul Davies and Stephen Fulling, each working slightly separately, each picking up a thread the others had left, was trying to find a cleaner way to understand what Hawking had done. And in the process, in the work of clarifying and rebuilding the argument from simpler foundations, the Unruh effect emerged. Not as the target, as a byproduct. As the thing you find when you dig for something else and discover you've been standing on something deeper all along. Fulling came first, in 1973, noticing that different observers define different vacua, that the vacuum is not a universal observer-independent thing, but depends on the coordinate system you're using. Davies, in 1975, working with moving mirrors and the radiation they produce, showed how a moving reflecting surface could create thermal radiation from the vacuum. And then Unruh, in 1976, gave it the sharp, clean form we recognize today, the acceleration-temperature relation. The precise formula, the physical picture of an accelerating observer immersed in a bath of particles at a temperature proportional to their acceleration. And William Unruh himself, a Canadian physicist working at the University of British Columbia, where he has spent most of his career, arrived at this by working backward from Hawking. By asking, if this is true for black holes, what is the simplest possible flat space version of the same thing? And finding that the flat space version was in some ways even cleaner than the black hole version. Because you didn't need curved spacetime at all. You needed only the quantum vacuum, and a horizon you could make from nothing but motion. That's where we are. You've travelled a long way tonight, and I mean that gently, because the road has been a careful one, and we have not rushed. We started with the puzzle, 2 observers, 1 patch of vacuum, opposite readings. We asked what it could mean, and we found that the answer lives in the question of what a particle is, in the observer-dependent way that quantum fields divide into modes, in the Bogoliubov transformation that translates one observer's language into another's and finds warmth where there seemed to be nothing. In the tiny, beautiful thought experiment of the Unruh DeWitt detector clicking quietly in the accelerated dark, and in the Rindler horizon, that wall of unreachable space-time that acceleration conjures out of geometry alone. And we found that the warmth isn't a trick. It's the warmth of a horizon, of separation, of having only half the correlations, of moving fast enough through empty space that the universe starts hiding things from you, and what you can still see glows. We have not yet talked about the numbers, about how warm and why so vanishingly cold that no one has ever caught it. We haven't talked yet about the beautiful, careful honesty of the situation, about what has been measured and what has only been predicted, about the experiments that have come the closest and the arguments about whether they count. We haven't talked about the petawatt lasers and the spinning electrons and the laboratories where physicists build imitation horizons in fluids and light and listen to them with instruments tuned to the same mathematics, trying to hear a thing they cannot yet hear in the vacuum itself. All of that waits. We'll get there, softly, in the time that remains. But tonight, this part, you have the foundation. You have the thing that makes everything else make sense. A particle is not a thing in a room. It is a statement about how the field looks to a particular observer, using their particular clock, measuring energy in their particular way. Two observers with different clocks can look at the same field and genuinely, honestly see different numbers of particles. And one way to get a different clock is simply to accelerate. So if you are lying there quietly, perhaps with a lamp still on, or in the deep quiet of a room that has gone dark around you, and you're wondering what it would be like to be the accelerating observer, the one who sees the warm glow where the other sees nothing. Here is what I can tell you. It would feel from inside exactly like being warm. Nothing more dramatic than that. Your instruments would detect particles where the person standing still would detect none. Your thermometer would read something just barely above absolute zero, so barely that no thermometer in the history of our species has ever been sensitive enough to see it. The effect would be real, and it would be yours alone. You would be warm in a vacuum that to everyone else looked completely empty. The void would be glowing, very faintly, just for you. And as you rest now, wherever you are, whatever time the room around you says it is, let that image stay. A patch of perfect emptiness. Two travelers, one warm, one cold. Neither of them wrong. That is the Unruh effect, in its quiet heart. And there is more to tell. But it can wait. So let's talk about the numbers, because that is where the story goes next, and they are, in their own quiet way, some of the most astonishing numbers in all of physics. Not because they are large in the dramatic sense, not because they describe the width of a galaxy or the age of the universe. They are astonishing because of what they tell you about the gap between a thing being real and a thing being detectable. A gap so wide it makes the effect almost poetic in its hiddenness. William Unruh, working through the mathematics in 1976, didn't just establish that an accelerating observer sees thermal particles where an inertial observer sees none. He wrote it down precisely. He gave you a temperature, and it is a temperature you can calculate right now with a formula that fits in one line. The Unruh temperature, the temperature the accelerating observer measures for the vacuum around them, is equal to a certain combination of 4 constants of nature multiplied by one variable. The variable is the acceleration. The constants are the reduced Planck constant, which you can think of as the smallest unit of action the universe will deal in, the currency of quantum events. The speed of light, the ceiling on how fast anything can travel through space, the Boltzmann constant, which is the translation rate between temperature and energy, The converter that lets you say a certain number of joules of kinetic energy in the atoms of a gas feels like a certain number of degrees. And the number 2 pi, the full turn of a circle, which appears here for reasons connected to the geometry of the horizon. These 4 constants are wrapped around the acceleration like a coat, and together they tell you, for every unit of acceleration you add, the temperature rises by this much. The precise relation is written T equals times A, divided by the whole quantity 2 pi times C times K sub B, where T is the temperature, A is the acceleration, is the reduced Planck constant, C is the speed of light, and K_B is the Boltzmann constant. It is a short formula, clean, almost spare. But when you put numbers into it, the real measured values of those constants, something remarkable happens. The answer comes out extraordinarily, almost heartbreakingly small. To warm the quantum vacuum by a single degree Kelvin, just 1 degree, the smallest whole number step on the scale that begins at the coldest possible temperature, you need an acceleration of roughly 2.5 times 10 to the power of 20 meters per second squared. Let me help you feel that number, because just reading it is not quite enough. Earth's gravity pulls you downward at about 9.8 meters per second squared. We call that 1g. It is what you feel lying in your bed right now, the gentle, constant insistence of the planet underneath you. That is 1g. 2.5 times 10 to the 20 meters per second squared is roughly 10 billion times 1g. Written as a number rather than a power, it is approximately a 1 followed by 20 zeros. 100 billion times the pull of Earth. For context, the most violently accelerating things we have ever built, the protons swung around the ring at CERN, the electrons spinning in particle accelerators at SLAC and Fermilab, achieve accelerations that sound impressive until you hold them beside this number. Even the most ferociously accelerated particles we have managed to push through our machines fall short of this threshold by many, many orders of magnitude. And all of that just for 1 Kelvin. Now run the formula the other way. Take the acceleration you feel lying still on the surface of the Earth, 9.8 meters per second squared. Put that into the Unruh formula. What temperature do you get? Approximately 4 times 10 to the negative 20 Kelvin. In ordinary language, 40 billionths of a billionth of a degree above absolute zero. If you wrote that number out in decimal form, you would write a 0, then a decimal point, then 19 more zeros, then a 4. The warmth of the vacuum that your body's gentle press against gravity is theoretically generating right now, in the sense that you are technically being accelerated upward by the floor beneath you, is a temperature so small it makes the coldest temperatures ever achieved in laboratories, and physicists have gotten very good at cold, within millionths of a degree of absolute zero. Look like a raging furnace. This is precisely why the Unruh effect has never been directly measured. It is not a matter of clever engineering or a better thermometer. It is a matter of fundamental scale. The number is below the noise of everything, below the thermal jitter of any object we could put into motion, below the residual heat of the microwave background radiation left over from the early universe, which fills all of space at about 2.7 Kelvin. A temperature of 4 times 10 to the negative 20 Kelvin would be buried so completely under all other thermal signals that extracting it directly from the noise is, with any technology we currently possess or can foresee, simply not possible. And yet physicists do not dismiss it. They do not treat it as a curiosity that might evaporate under scrutiny. They take it seriously, deeply seriously, in the way you take something seriously when its denial would unravel the foundations of your best understanding of the world. We will come back to that, to why the theoretical confidence is so high even without a direct measurement. But for now, let the scale of the number settle. The vacuum glows for the accelerating observer. It glows at a temperature fixed precisely by the mathematics of quantum fields and the geometry of acceleration. And it glows so faintly at any acceleration a human being or a machine could survive or sustain that the glow has stayed invisible to every instrument we have ever built. That is honest. That is the state of the science. And there is something almost restful about it, the idea of a real warmth, genuinely there by the logic of the laws of nature, too faint to touch, drifting just beneath the floor of the measurable. Let it be there. Now, there is something that will help you understand why physicists are so confident in this number, despite never having measured it directly. Something that puts the Unruh effect in a much wider frame. Something that, when I tell you it, will probably make the whole thing feel less like a strange, isolated quirk and more like one face of a much larger truth. It has to do with black holes. Specifically, it has to do with a paper published in a journal called Nature in 1974 by a physicist named Stephen Hawking. The paper was short. It was 2 pages. And in those 2 pages, Hawking made a claim so unexpected that many of his colleagues, when they first heard it, assumed he had made a mistake. He claimed that black holes are not black. Let me explain what that means, and why it matters, and how it leads straight back to William Unruh and the warm glow in the vacuum. A black hole, as you may know, is a region of space where gravity has become so intense that nothing, not matter, not light, nothing at all, can escape if it crosses the boundary. That boundary has a name, the event horizon. It is not a surface you could stand on or touch. It is a surface in the geometry of space and time, a point of no return. The place where escape velocity reaches the speed of light and then keeps going up, so that even moving at the speed of light you could not get out. For a very long time it was thought that this made black holes essentially permanent. Once something fell in, it stayed in. The black hole could only grow, absorbing matter and energy from its surroundings, never losing anything. If a black hole stopped receiving new matter, it would simply sit there forever, cold and dark and unchanging. Hawking showed this was wrong. He showed, using quantum field theory, the same framework that underlies the Unruh effect, that the quantum vacuum right at the edge of a black hole horizon is not simply quiet. Because of the way the horizon curves space and time, and because of the way the quantum fields respond to that curvature, the black hole radiates. It emits particles, thermally with a specific temperature. The Hawking temperature of a black hole is equal to the reduced Planck constant times the cube of the speed of light, divided by the quantity 8 pi times Newton's gravitational constant, times the mass of the black hole times the Boltzmann constant. Written in the shorthand, T sub h equals times c cubed over 8 pi times g times m times k underscore b. There is a beautiful and slightly unsettling feature of this formula. The temperature goes up as the mass goes down. A very massive black hole, say, the one at the center of our galaxy, millions of times the mass of our sun, has a Hawking temperature so small it makes the Unruh temperature at 1G look warm by comparison. Unimaginably cold. Far below the temperature of the cosmic microwave background, but a very small black hole, a primordial one, if such things exist, formed in the early chaos of the universe at subatomic scales, would be hot. And as it radiated, it would lose mass, so it would get hotter, so it would radiate faster, and so on, in a runaway that ends in a final burst of radiation. Black holes, Hawking said, evaporate. Now, you might be wondering, what does this have to do with Unruh? The Unruh effect is about flat space. There is no black hole in it, no mass, no gravity, no dramatic curvature, just a very empty region of perfectly ordinary space-time, and an observer who happens to be accelerating. And here is where the connection becomes something more than a coincidence. Think about what it means to be an observer who hovers just outside a black hole's event horizon. Not one who has fallen in. That observer crosses the horizon quietly, and depending on the mass of the black hole, might not even notice the moment of no return. No, think instead of an observer who wants to stay fixed in space, just outside the horizon, who wants to resist the pull of gravity and remain at a constant distance from the event horizon, neither falling in nor flying away. To stay still like this, in a gravitational field, you must accelerate. You must fire engines. You must push against gravity constantly. Any object sitting still in a gravitational field is, in the language of general relativity, actually being accelerated, pushed away from the free fall path it would naturally follow. When you sit in your chair, you are being accelerated upward at 1g by the chair's support. When you float freely in orbit, you are in free fall, and your acceleration is 0. So an observer hovering just outside a black hole's event horizon is an accelerating observer, and the acceleration required to hover at a particular distance above the horizon has a specific value, one you can calculate from the mass of the black hole and your distance from the event horizon. Now apply the Unruh formula to that acceleration. What you get, the Unruh temperature for that specific acceleration, matches the Hawking temperature of that black hole, adjusted for how far you are from the horizon. They are the same, not approximately, not as an analogy, mathematically the same. The warm thermal glow that Hawking says pours out of the black hole is from the perspective of an observer forced to accelerate just to stay in place outside the horizon, simply the Unruh effect. The accelerating observer near a black hole is the accelerating observer in empty flat space, run through the same calculation. The quantum vacuum, disturbed by the horizon's presence, the quantum vacuum, disturbed by the acceleration's horizon, they speak the same mathematics. Unruh is Hawking, in flat space. Or, if you prefer the other direction, Hawking radiation is the Unruh effect, curved. And the bridge between them, the thing that makes this equivalence not just a mathematical curiosity, but a deep statement about how the universe is built, is one of the oldest ideas in relativity. It is Einstein's equivalence principle. The equivalence principle, in its simplest form, says this: you cannot tell the difference between being in a gravitational field and being in an accelerating frame of reference. At least, not locally, not in a small enough region of space over a short enough time. If you wake up in a sealed room with no windows and feel yourself pressed to the floor, you cannot know whether you are sitting on a planet or whether the room is in a rocket accelerating upward at exactly 1g. The experience is identical. The physics is identical. Locally, gravity and acceleration are the same thing. Einstein understood this in 1907 before he had general relativity. He called it the happiest thought of his life, and it is the seed from which general relativity grew, the idea that gravity is not a force pulling things together, but a curvature in the geometry of space and time, so that what looks like a gravitational pull from one perspective looks like the natural path through curved geometry from another. The equivalence principle is the reason the Unruh effect and Hawking radiation are connected so deeply. Acceleration and gravity are locally equivalent. The Unruh effect is about acceleration. Hawking radiation is about gravity. The equivalence principle says they must be two views of the same thing. And they are. This is why, even without a direct measurement of the Unruh temperature, physicists do not lose sleep, in the ordinary sense, over whether it is real. Hawking radiation and the Unruh effect are not two separate predictions you might accept or reject independently. They are woven together. To deny the Unruh effect, you would need to also undo the mathematics behind Hawking radiation, and behind the equivalence principle, and behind the deep structure of quantum field theory in curved spacetime. They are one piece. The Unruh temperature is not an isolated guess. It is a consequence, perhaps the cleanest, most startling consequence, of the framework that holds all of this together. If you are resting now, and you want a way to hold this lightly as you drift, here it is. Acceleration and gravity are the same thing. A horizon made of motion and a horizon made of mass are the same kind of thing. The warm glow an accelerating observer feels in the vacuum and the warm glow that leaks from a black hole are the same kind of warmth. It is as though the universe has one rule written very deep, and you can see it from two sides depending on how you look. Now let me tell you how all of this was found. Because it did not arrive fully formed, it was discovered in pieces by different people across the space of a few years in the early 1970s, and none of them set out to find it. It emerged as a kind of unplanned consequence of trying to understand something else. The story begins with a physicist named Stephen Fulling. Fulling was working in the early 1970s on a problem that sounds technical and will turn out to be the seed of everything. The question he was asking was essentially this: if you take the ordinary quantum field theory we use in flat spacetime, in Minkowski space, the geometry of special relativity where there is no gravity and space and time are as simple as they ever get, and you try to reformulate it from the perspective of a uniformly accelerating observer, do you get the same physics? The accelerating observer has a different coordinate system. They slice up space-time differently. What they call space and time are different from what an inertial observer calls space and time. These coordinates have a name, Rindler coordinates, after the mathematician Wolfgang Rindler, who studied this geometry. And Fulling found something surprising. When he wrote the quantum field theory in Rindler coordinates, and then tried to define what a particle was, what the ground state, the vacuum, looked like, he got a different answer than the inertial observer. The inertial observer's vacuum and the Rindler observer's vacuum were not the same vacuum. Fulling published this in 1973, and it was a real discovery, an important one. But it was somewhat abstract. It showed the vacua were different without fully spelling out what that meant physically. The next step came from Paul Davies. Paul C. W. Davies, working in 1975, took the idea further by considering a related problem, a moving mirror in a quantum field. When a mirror moves, when it accelerates through space, the quantum field reacts to the mirror's surface in a way that depends on the acceleration. Davies showed that an accelerating mirror emits radiation, thermal radiation, and he connected this, carefully and precisely, to the new notion that accelerating observers define particles differently. Davies was extending and clarifying what Fulling had found. He was showing that the difference wasn't just a mathematical artifact, it had physical consequences. An accelerating object would genuinely experience a thermal bath of particles. And then, in 1976, William Unruh wrote the paper that is now considered the definitive statement. William G. Unruh is a Canadian physicist based at the University of British Columbia in Vancouver, and in 1976 he was not primarily trying to understand accelerating observers for their own sake. He was trying to understand Hawking radiation. Hawking had published his result in 1974-75. It was extraordinary and somewhat mysterious. The mechanism involved quantum fields near the event horizon, and the technical details were subtle enough that even experts were unsure exactly how to think about them. Unruh wanted a cleaner way to see what Hawking had found, a simpler model that might illuminate why a horizon produces thermal radiation. And in working through this, he found the flat space version of the same result. He showed clearly and precisely that a uniformly accelerating observer in ordinary flat spacetime, no black hole, no gravity, nothing exotic, would detect a thermal bath of particles at a temperature given by the formula we now call the Unruh temperature. The paper he published was called Notes on Black Hole Evaporation. It appeared in Physical Review D, Volume 14, in 1976. And it was, in a sense, a note. A technical paper working out the details, but the implications were, and remain, extraordinary. So the sequence is, Fulling, in 1973, who noticed the vacua were different. Davies in 1975, who connected the difference to thermal radiation from moving mirrors. Unruh in 1976, who gave the clean general statement, an accelerating observer sees a thermal bath at a temperature proportional to the acceleration, and that temperature is exactly the flat space cousin of the warmth that glows from a black hole. The effect carries all three names. Physicists sometimes call it the Fulling, Davies, Unruh effect, the FDU effect. The full story has 3 chapters and 3 authors. But in common usage, the shorthand of the field, it has mostly become the Unruh effect, in the same way that a piece of mathematics is often remembered by one name, even when several hands shaped it. What is worth pausing on is that none of them set out to discover a warm vacuum. They were working backwards from Hawking's black hole, trying to understand why a horizon produces radiation. The Unruh effect was not a prediction made and then confirmed. It was a consequence found by following the mathematics into unfamiliar territory and then recognized for what it was. This happens often in theoretical physics. The most important discoveries are sometimes not the thing you were looking for, but the thing you found along the way. Hawking was trying to understand whether black holes could radiate. Unruh, trying to understand Hawking, discovered something more fundamental, that thermal radiation from a horizon is not an exotic property of black holes, but a basic feature of how accelerating observers experience quantum fields. The vacuum temperature is not a special effect of black hole gravity. It is what acceleration does, generally, to the quantum field. Unruh's work was rapidly absorbed into American theoretical physics. The connection to Hawking radiation made it immediately relevant to anyone working on quantum gravity, which, in the late 1970s, was a very active field, drawing on researchers at institutions across the United States. The black hole physics community and the quantum field theory community were, in those years, in deep conversation. Papers moved fast. Ideas crossed from Canada to Berkeley to Princeton to Chicago in months. The Unruh temperature became a standard result, something graduate students were expected to derive, something that appeared in textbooks within years of the original paper. Birrell and Davies, Nicholas Birrell and Paul Davies, the same Davies who had contributed to the story, published a textbook in 1982 called Quantum Fields in Curved Space. It is one of the foundational references for anyone who wants to understand quantum field theory in the presence of gravity or acceleration. The Unruh effect is there, derived carefully, placed in its full context. Robert Wald at the University of Chicago published a text in 1994, Quantum Field Theory in Curved Spacetime and Black Hole Thermodynamics, that cemented the theoretical framework still more firmly. The Unruh temperature, the Hawking temperature, the equivalence principle connection, all woven into a rigorous and beautiful structure. By the 1990s, the Unruh effect was not a fringe result, it was a standard piece of the edifice. Not confirmed in the laboratory, it has never been confirmed directly in the laboratory, but theoretically established with a confidence that mirrors, in some ways, the confidence physicists feel about results they have measured. Because the mathematics does not have loose ends. Every approach to the problem converges on the same answer. And here is where I want to linger for a moment, because this might be the question settling gently at the back of your mind. If we have never measured it, if the temperature is too small, if no thermometer has ever ticked in response to the Unruh glow, then how sure are we really? The answer lives in a particular kind of confidence that theoretical physics develops about certain results. Not the confidence of measurement, which is strong and direct and clean. A different kind. The confidence of many independent paths leading to the same place. The Unruh temperature was first derived by the method Unruh used in 1976, analyzing what the accelerating observer's particle detector clicks to. That is one path. But the same temperature emerges from a completely different analysis called the Bisogniano-Wichmann theorem. J. Bisogniano and Eivind Wichmann were mathematical physicists working in axiomatic quantum field theory, the branch of the subject concerned with proving things rigorously from first principles with full mathematical precision. In 1975 and 1976, they proved a theorem about the algebraic structure of quantum field theory and its restriction to a wedge of spacetime, exactly the wedge an accelerating observer can access. And their theorem, derived by entirely different methods, gives the same Unruh temperature. A third path runs through what is called the KM's condition, named after the physicists Kubo, Martin, and Schwinger. The KM's condition is a precise mathematical criterion for a quantum state to be in thermal equilibrium. If you want to know whether a quantum state is genuinely thermal, genuinely at some temperature, you ask whether it satisfies the KM's condition. When physicists examine the Minkowski vacuum from the Rindler observer's perspective, it satisfies the KM's condition at exactly the Unruh temperature. It is genuinely thermal, not approximately, not as a special limit. It passes the rigorous test for thermal equilibrium. 3 independent derivations, 3 different mathematical traditions, particle detectors, axiomatic quantum field theory, thermal equilibrium conditions, all arriving at the same formula. There is also something called the Unruh DeWitt detector, named for both Unruh and the physicist Bryce DeWitt, who formalized the model. A DeWitt detector is a simple idealized object. You can think of it as a 2-level quantum system, a thing that can be in a ground state or an excited state, like an atom with exactly 2 energy levels. You drag this detector along an accelerated path through the vacuum. In the inertial vacuum, if the detector were moving at constant speed, it would stay in its ground state. Nothing would happen. The vacuum, to a non-accelerating detector, is really empty, But when you drag the detector along an accelerated path, it gets excited. It clicks, in the sense that it spontaneously jumps to its excited state, as though it had been immersed in a bath of thermal radiation at the Unruh temperature. The Unruh DeWitt detector is not a real device you can build and put in a rocket. It is a mathematical model, an idealization designed to ask the question cleanly: what does an accelerated thing experience? And the answer it gives is warmth at precisely the Unruh temperature. Together, these four approaches, Unruh's original derivation, the Bisogniano-Wichmann theorem, the KM's condition, and the Unruh DeWitt model, constitute a kind of convergent evidence that, in theoretical physics, is taken as grounds for very high confidence, not certainty in the experimental sense, but the kind of structural certainty you feel when four different roads, starting from very different places, all arrive at the same town. To deny the Unruh effect would not merely mean saying that one derivation was wrong. It would mean untangling all four. It would mean finding the flaw in axiomatic quantum field theory, in the thermal equilibrium criterion, in the black hole connection, in the detector model. And then it would mean explaining why, despite all of that unwrapping, the Hawking temperature still works. Because Hawking radiation and the Unruh effect are stitched together. To pull out one thread is to pull out both. Physicists therefore speak of the Unruh effect the way they speak of other theoretical certainties that happen to be practically unmeasurable. Not as a guess or an extrapolation, but as a load-bearing piece of the structure. Remove it, and the structure changes its shape. The effect is, in the language of the field, robust. And in a way, there is something comforting in this. The universe is not waiting for us to measure the Unruh temperature to decide whether it is true. The mathematics has already worked it out. The consistency is already there, woven in. We are simply too large, too slow, too warm ourselves to see the glow. Let all of that settle now, as gently as it came. You are somewhere in the quiet, and outside whatever window your room has, or doesn't have, the world is doing what worlds do at this hour. And in the space between you and that window, in the perfectly ordinary air, and in the perfectly ordinary vacuum that underlies it, in every region of space not occupied by any particle or wave of light, the quantum fields are doing what they always do. Fluctuating, sitting in their lowest energy state, being the most empty thing it is possible to be, while still being something. If you accelerated hard enough through that space, your thermometer would tick. Not noticeably, not measurably, with anything we have built, but by the logic of quantum field theory, by the clean mathematics that connects Fulling's observation to Davies's moving mirror, to Unruh's flat space derivation, to Hawking's black hole glow, by the equivalence principle that has been the spine of our understanding of gravity for 100 years. By all of that, the reading would be above absolute zero. The void would be warm in a way that belongs to you alone. And the temperature, that extraordinary hidden number, is fixed, not by any property of the space itself, not by anything the space is doing, fixed purely by how fast you are accelerating through it. Which means, quietly, the temperature is yours. Not the vacuum's. That is the thing. The warmth is not in the space. The warmth is in the relationship between the space and your motion. We are approaching now the part of this story that I find the most genuinely strange, not the formula, not the numbers, not even the horizon made of nothing but motion, but what it all means, what it says about the most basic things we might believe about space and the stuff in it. But that is for the next part of the journey. And there is no hurry. The night is long enough. For now, let the three names rest with you, Fulling, in 1973, who noticed the vacua were different. Davies, in 1975, who saw that the difference radiated. Unruh, in 1976, who gave it the clean formula and the clean name and tied it back carefully to the black hole glowing at the end of Hawking's calculation. And Hawking himself, in 1974 and 1975, who did not know, quite, that he had found the curved space version of a flat space truth. Who found his answer by following the quantum fields to the edge of the horizon and listening to what they said. They were all, in some sense, looking at the same horizon from different sides. The edge of what can be seen. The place where the field must reorder itself according to a different observer's geometry. The place where the vacuum stops being the same for everyone. There is something almost meditative about that image, if you let it be. The horizon that divides what is accessible from what is not. The horizon made of mass and gravity. The horizon made of pure motion and acceleration. Both of them warm at the edge. Both of them producing, from the quantum fields that permeate the empty space on their bright side, a faint thermal glow that belongs to the observer who feels them. You, lying very still right now, are in a gravitational field. The Earth is below you. The equivalence principle says that being held still against the pull of gravity is, locally, the same as being in an accelerating frame. Your acceleration relative to freefall is 1g. Your Unruh temperature is 4 times 10 to the negative 20 Kelvin. You are the accelerating observer. And the vacuum around you, by the logic of the physics, is very, very, very faintly warm. Just for you. Sleep well, if the warmth finds you before the words do. There is still more to tell about the attempts to measure it, about the electrons in the great rings of particle accelerators and what their spin polarization might reveal, about the petawatt lasers that could push electrons hard enough to bring the Unruh temperature towards something almost visible, about the clever laboratory systems built of sound and light and ultra-cold gas that test the same. Mathematics by other means, and all of it is waiting. But there is no hurry. It will be here. And so we arrive at the question that has been sitting quietly underneath everything we have explored together tonight. The natural question, the one that a careful mind will always reach sooner or later. We have spent a long time inside the mathematics, inside the philosophy, inside the strange geometry of horizons made of nothing but motion. And you may have noticed that, for all its elegance, for all its internal consistency, for all the ways this prediction seems to be telling us something genuinely true about the fabric of the world, we have not yet said the word measured. That is not an accident. So let us sit with that for a moment. Let us be honest about it, the way good physics deserves to be. The Unruh effect, the Fulling-Davies Unruh effect, with its clean formula and its staggering numbers, this is a prediction. A theoretical prediction. A prediction that sits within quantum field theory and general relativity the way a load-bearing column sits within a building. Remove it, and the walls come down. But it is, as of the moment these words reach you, experimentally unconfirmed. No one has ever placed a thermometer in empty space, accelerated it hard enough, and watched the temperature rise from the quantum vacuum alone. And the reason, as we touched on earlier, is simply that the numbers are almost unreachably small. Think of the formula again. T equals A over 2 times C times K underscore B. Everything in the denominator is a constant of nature. The only thing you can change is the acceleration. and you need approximately 2.5 times 10 to the 20 meters per second squared just to push the apparent temperature of the vacuum up by a single Kelvin. 1 degree. That is roughly 10 billion times the acceleration of gravity at Earth's surface. A spacecraft re-entering the atmosphere at its most violent pulls maybe 40 or 50 G. An artillery shell may be 10,000. An electron slammed against an electric field inside a conventional accelerator may be 10 to the 15. None of these come close. Even the most violent physical accelerations we have ever produced in a laboratory fall short of what would be needed by many orders of magnitude. At the surface of the Earth, where you are lying right now, the Unruh temperature of the vacuum around your body is approximately 4 times 10 to the negative 20 Kelvin. That is 4/100th of a billionth of a degree above absolute zero. We do not have a thermometer sensitive enough to resolve that against the background noise of the universe around it. We do not even come remotely close. So the honest answer to has anyone measured this is no. But then, and this is the part that actually matters, why do physicists take it seriously at all? Because the mathematics that produces the Unruh effect is not a single delicate calculation that might have a hidden error. It is a result that falls out of quantum field theory along several completely independent paths. And when independent roads arrive at the same destination, that is not a coincidence. That is the structure of the landscape. Let us walk those roads slowly, one at a time. The first road is the one William Unruh himself took in 1976, the direct calculation of what an accelerated detector actually measures. Not an abstract thermometer, but a specific model. Bryce DeWitt, working with Unruh's framework, formalized what is now called the Unruh-DeWitt detector. Imagine the simplest possible measuring device: 2 energy levels, a ground state and an excited state, like the 2 states of a single atom. You couple this tiny device to the quantum field around it and then drag it along an accelerated path through flat, empty space. What does it do? It gets excited. It clicks. It transitions upward from its ground state to its excited state, spontaneously, as though it were sitting in a warm bath of radiation. And the rate at which it clicks follows a thermal distribution, the precise statistical fingerprint of heat at exactly the Unruh temperature corresponding to its acceleration. Not approximately. Exactly. The Unruh-DeWitt detector is not a real physical device you can build and test tomorrow. It is an idealized model. But its behavior emerges rigorously from the quantum field theory equations, and what it tells you is that the thermal bath is not a metaphor. A simple 2-level system dragged fast enough through empty flat space would genuinely behave as though it were immersed in warm radiation. The mathematics is unambiguous. That is one road. The second road is more abstract and, in its own way, more beautiful. In the physics of thermal equilibrium, in the theory of systems that have settled into a steady, stable warmth, there is a mathematical condition that tells you when a state is truly thermal. It is called the KM's condition, after Ryogo Kubo, Paul Martin, and Julian Schwinger, who identified it in the late 1950s and early 1960s. The KM's condition is a precise statement about the correlation functions of a quantum field, about how measurements made at one time relate to measurements made at another, and it has a specific, recognizable signature that appears only in thermal states, not in arbitrary quantum states. When you take the Minkowski vacuum, the ground state of the quantum fields as an inertial observer sees it, and you ask what it looks like when viewed through the window of an accelerated observer, it satisfies the KM's condition. Exactly, precisely. The accelerated observer's version of the vacuum passes the thermal test. Not because anyone arranged it that way, but because of the deep mathematical structure connecting Minkowski time and Rindler time. The vacuum is, from the accelerated observer's perspective, a proper thermal state in the rigorous technical sense of the word. It is not just warm in some hand-waving way, it is thermally equilibrated according to the strictest mathematical definition available. That is the second road. And the third road is perhaps the most powerful of all, because it does not even begin from the specific physics of the vacuum or of acceleration. It begins from pure mathematics, from the axiomatic foundations of quantum field theory itself. In 1975 and 1976, Joseph Bisognano and Eivind Wichmann proved a theorem, the Bisognano-Wichmann theorem. That works at a very deep level. They were not thinking about black holes or accelerated observers or thermometers in space. They were doing rigorous mathematical physics, studying the algebraic structure of quantum field theories and the properties of the vacuum state. And what they found, emerging from the axioms alone, was this: the vacuum state of any well-behaved quantum field theory. When restricted to a wedge-shaped region of space-time, the region accessible to an accelerated observer has exactly the properties of a thermal state. The temperature, when you work it through, is the Unruh temperature. The Km's condition is satisfied. The thermal character is not assumed, it is derived from first principles. The Bisognano-Wichmann theorem does not know about acceleration. It does not know about thermometers or detectors or black holes. It knows about algebra and axioms and the structure of quantum fields, and it arrives at the same thermal bath. 3 roads: the detector calculation, the CM's thermal condition, the axiomatic theorem. All 3 point to the same result from different starting places, using different mathematical tools. That is why physicists trust the Unruh effect even without a direct measurement. You would have to break 3 independent pillars of quantum field theory to make it go away. And if those pillars break, the whole structure, the entire framework of physics as we understand it, breaks with them. The Unruh effect is not a fragile outlier clinging to a single chain of reasoning. It is woven into the fabric of the theory at multiple levels. And yet, it has never been directly confirmed. The honest physicist holds both of these things at once, without letting either cancel the other. So the question, the one that keeps theoretical physicists up at night, which is perhaps not the ideal quality in a sleep video topic, but here we are, is whether there is any path at all toward testing it. Any experiment, however indirect, that might at least catch the shadow of the Unruh effect passing by. As it turns out, there are several proposals. None of them is clean, all of them are contested, or limited, or both. But they are worth walking through, because each one is a story in itself. The most tantalizing comes from an unlikely source, from electrons in a ring. In 1983, 2 physicists published a paper that made a quiet but striking claim. Their names were John Bell and John Magne Lenas. John Bell you may know from another context. He is the same John Bell who in 1964 devised the Bell inequalities, the elegant test that eventually showed the world that quantum entanglement is real, not a hidden variable trick. Bell was at CERN, the great accelerator laboratory in Geneva. Linus was at the University of Oslo. Together, they noticed something. When electrons travel in a circle inside a particle storage ring, and they do travel in circles, kept curved by strong magnetic fields, they are constantly accelerating. Not in a straight line, but centripetally, always being pushed toward the center of the curve. The accelerations involved are enormous. Electrons in a high-energy storage ring can experience centripetal accelerations of 10 to the 20 meters per second squared or more, comparable in order of magnitude to what the Unruh formula demands for a temperature of a fraction of a Kelvin. Bell and Linnaeus argued that this acceleration should have a real physical consequence. Electrons have a property called spin, a kind of intrinsic angular momentum, which you can think of loosely as a tiny internal compass needle that can point either along or against the direction of a magnetic field. In a storage ring, a beam of electrons gradually becomes spin-polarized over time. The spins drift toward alignment with the magnetic field through a mechanism worked out by Arseny Sokolov and Isaac Turnov in 1963. The Sokolov-Turnov effect. In principle, given enough time, the polarization should approach a fixed limit, and it does approach that limit, but never quite to the theoretical maximum. Bell and Linnaeus pointed out that the Unruh thermal bath experienced by the circulating electrons would disrupt the spin polarization. A warm bath means random kicks, random excitations, and a thermal bath at even a tiny temperature will prevent the spins from aligning completely. The equilibrium polarization level would be reduced by a calculable amount, and when they compared their prediction to real data from real storage rings, they found agreement. The actual polarization levels observed in electron storage rings at SLAC in California, at CERN in Switzerland, at other facilities around the world are consistent with the Unruh correction. That is remarkable, if you sit with it. The electrons in those great rings, whipping around their circular paths millions of times per second, might be showing us the shadow of the Unruh effect in the only form we can currently reach. But, and this is important, and honest physicists are careful about it, the situation is contested. The difficulty is that circular acceleration is not quite the same as the ideal case in the Unruh calculation. The pure, clean Unruh effect is derived for uniform linear acceleration, a perfectly straight path with constant proper acceleration forever. Circular motion is different geometrically. The Rindler horizon that we spoke of earlier, the clean causal boundary made of motion alone, does not form in quite the same way for circular paths. The relationship between circular acceleration and the thermal bath is more complicated, and different physicists reading the same equations have sometimes reached different conclusions about whether the spin polarization argument is truly an Unruh signature or merely a related but distinct effect that happens to give similar numbers. So the Bell-Linnaeus argument is suggestive, deeply suggestive. But it is not a confirmed detection. It is contested in the careful, productive way that good physics is supposed to be contested. It is a thread that points in the right direction without tying the knot. Still, at SLAC and Fermilab and the other great accelerator communities, this thread is taken seriously. The storage ring behavior of electrons is real data, and it is real data that the Unruh framework predicts correctly. That counts for something, even when it falls short of certainty. The second proposal is newer and more dramatic and turns on the extraordinary machines built for a different purpose entirely. In 1999, two physicists, Pisin Chen at SLAC and Toshiki Tajima, then at the University of Texas at Austin, published a proposal in Physical Review Letters. Their idea was to use ultra-intense laser pulses to accelerate electrons to the necessary scale. The laser technology that makes this conceivable is sometimes called petawatt class or high-intensity laser physics. The basic idea is to compress an enormous amount of optical energy into an extraordinarily short pulse. pulses lasting quadrillionths of a second, and then focus that pulse to a tiny spot. The electric field strengths at the focus can be astonishing. An electron placed in such a field would be kicked so violently that its acceleration, for the duration of the pulse, might reach somewhere between 10 to the 25 and 10 to the 30 meters per second squared. Let those numbers settle for a moment. 10 to the 20 meters per second squared per Kelvin of Unruh temperature, and laser-accelerated electrons potentially reaching 10 to the 25 or beyond. That is a factor of 100,000 beyond the threshold for a single Kelvin. In principle, the Unruh temperature for such an electron would not be a tiny fraction of a degree above absolute zero. It might be tens of thousands of degrees above absolute zero. Chen and Tajima proposed that an electron accelerated by a petawatt laser should emit radiation, Unruh radiation as they called it, in ways that could distinguish it from ordinary electromagnetic radiation. If the electron is genuinely sitting in a thermal bath of vacuum particles, its emission spectrum should carry a thermal signature that differs from what classical electromagnetism alone would predict. The proposal is real. The physics is serious. But an actual experiment with the necessary precision has not been carried out. The technical challenges are enormous. The signal is buried in a welter of other radiation processes that happen when electrons are accelerated to extreme energies. Separating the Unruh signature from all the other things happening simultaneously in a petawatt laser interaction is a formidable problem. The laboratories with the tools to attempt it, and several are now approaching the relevant intensity scales, are actively working on it. So this too is a thread being pulled carefully by serious physicists with serious instruments, but not yet a confirmed result. And then there is the third path, the most indirect of all, and in some ways the most beautiful. If you cannot reach the acceleration directly, you can perhaps test the mathematics by building something that obeys the same equations in a different physical setting. This is the idea behind analog gravity. If the Unruh effect and Hawking radiation emerge from the mathematics of quantum fields near horizons, then any system that has a mathematical horizon, a point beyond which signals cannot propagate, might show the same thermal emission. Not the vacuum effect itself, but the same fundamental prediction dressed in different physics. The most elegant analog is sound in a flowing fluid. If a fluid flows faster than the local speed of sound in one region and slower in another, there is a boundary, a sonic horizon, beyond which sound waves cannot propagate upstream. From the point of view of sound, that boundary behaves like a black hole horizon. And the quantum theory of sound in that fluid, the quantum fluctuations of the density waves, should produce a thermal spectrum of sound radiation analogous to Hawking radiation, with a temperature set by the gradient of the flow at the horizon. The same mathematics, different medium. You can build this in a laboratory, and people have. Jeff Steinhauer, a physicist at the Technion, the Israel Institute of Technology in Haifa, spent years building an acoustic black hole out of a Bose-Einstein condensate. A Bose-Einstein condensate is a state of matter in which a gas of atoms is cooled to temperatures close to absolute zero until the atoms lose their individual identities and merge into a single quantum object, a superfluid, behaving collectively as one enormous quantum entity. In such a superfluid, excitations travel as sound waves, phonons, at a well-defined speed that depends on the density of the condensate. By shaping the flow of the condensate with precisely controlled laser beams and magnetic fields, Steinhauer created a region where the flow speed exceeded the local phonon speed, a sonic horizon. And then he watched it. In 2016, Steinhauer published a paper in Nature Physics reporting the observation of what he called analog Hawking radiation, a thermal spectrum of phonon pairs spontaneously created at the sonic horizon, with temperatures consistent with what the analog Hawking formula predicts. The pairs are created in the same way that the original Hawking calculation produces particle pairs at a real event horizon. The vacuum fluctuations of the phonon field straddling the horizon get separated, one falling in and one escaping, and the escaping one carries a thermal spectrum. The result was significant. It was also scrutinized intensely. Some physicists wondered whether the thermal spectrum Steinhauer observed could be fully accounted for by classical density fluctuations in the condensate rather than requiring a quantum explanation. Steinhauer refined and extended his measurements, and in 2019 published a follow-up in Nature, reporting stronger evidence for the quantum nature of the correlations. The phonon pairs showed entanglement signatures consistent with there being genuine quantum pairs produced at the horizon, not classical noise. It is not the Unruh effect in a vacuum. It is not Hawking radiation from a real black hole. Steinhauer would be the first to say so. The condensate is doing something analogous, obeying the same mathematics in a different physical medium, and observing the analog does not confirm the original. But it tells us something real and important: the mathematical machinery. The part that predicts thermal radiation from horizons based on quantum field fluctuations does seem to produce thermal radiation when you build a system that satisfies its conditions. The framework is, at the very least, not wrong. Similar experiments have been carried out with other analog systems: water waves flowing down channels with carefully shaped profiles, creating hydraulic horizons; optical analogues, using pulses of light in specially designed fibers where the local propagation speed can be made to vary. All of these test the same underlying quantum field horizon mathematics in accessible physical settings. The community that has gathered around analog gravity is spread across Europe, Israel, North America. Labs in the United States, at universities and at national facilities with connections to the broader SLAC and Fermilab accelerator communities contribute to the theoretical and experimental conversation. The goal is not to trick anyone into thinking the vacuum effect has been confirmed. The goal is to understand the mathematics deeply enough, in enough different physical contexts, that when an experiment finally becomes sensitive enough to probe the real vacuum, we will know exactly what we are looking at. And that may happen. Laser technology continues to advance. The next generation of high-intensity laser facilities being built now in France, in Romania, in China, in the United States will reach intensities that were not possible when Chen and Tajima wrote their proposal in 1999. The relevant parameter space is being approached slowly but measurably with every new generation of equipment. So where does that leave us? The Unruh effect is predicted by quantum field theory. It emerges from at least three completely independent mathematical derivations: the detector calculation, the KM's thermal condition, and the Bisognano-Wichmann theorem. It is supported indirectly by the electron spin polarization behavior in storage rings, though whether that truly counts as evidence is a matter of active debate. It is tested in spirit in the same mathematical structure by the analog gravity experiments in Bose, Einstein condensates and flowing fluids, and it has never been directly confirmed. That combination, robust theoretical prediction, contested indirect hints, no direct measurement, is not a comfortable place for a physicist to live. But it is the honest place, and it is, in a deeper sense, one of the most interesting places in all of contemporary physics. Because the Unruh effect is not a small technical detail that sits quietly at the edges of the theory. It is connected to the heart of what quantum field theory is saying about the nature of empty space. And it is connected through Hawking radiation, through the equivalence principle, through the mathematics of horizons, to the outstanding questions about black holes, about information, about what happens when general relativity and quantum mechanics are finally woven into a single coherent picture of reality. The resolution of those questions will almost certainly require the Unruh effect to be real, or it will require understanding exactly why it is not, in which case the new physics that replaces it will be even stranger. Either way, the question of whether empty space feels warm to an accelerating observer is not a peripheral puzzle. It sits near the center of what we do not yet fully understand. There is something comforting in that, if you are willing to look at it the right way. The universe has held certain mysteries back, behind a veil of extreme conditions we cannot yet reach with our instruments. And the fact that we know, with genuine rigor and mathematical confidence, what we would find if we could reach them, is itself a kind of triumph. We have reasoned our way to the edge of what we can observe, and we have looked over that edge, not with guesses or intuitions, but with equations that have passed every test we could apply to them. We cannot yet touch the warmth of the accelerated vacuum, but we know the temperature it would read. And now, having walked all the way through the mathematics and the history and the proposals and the honest limits of what we know, let us step back. Let us look at what this strange prediction has actually told us. We started tonight with two observers, one standing still, one accelerating, both looking at the same patch of perfectly empty space, one measuring absolute cold, a true quantum vacuum, as empty as the laws of physics allow, the other watching their instruments fill with a faint, soft, thermal hiss. Neither of them wrong. Neither of them confused or mistaken or pointing a broken instrument at the sky. We have now seen why. A particle, what we casually call a particle, as if it were an obvious, self-evident thing, a little marble sitting in space waiting to be counted, is not that. A particle, in quantum field theory, is a particular pattern, a particular vibration, in the quantum fields that fill all of space. And the definition of that pattern depends on how you divide the field's modes into positive and negative frequency, which depends on how you define time, which depends on how you are moving. The inertial observer, gliding steadily through space with no acceleration, uses one natural way of defining time and frequency. The accelerating observer, pressed back against their seat by the force of constant acceleration, uses a different one. The Bogolyubov transformation connects the two, and in connecting them, it reveals that what looks like a vacuum, zero particles, total emptiness, to the first observer looks like a warm bath of particles to the second. Neither observer is seeing an illusion. Neither is being fooled. They are genuinely inhabiting different descriptions of the quantum field, and both descriptions are valid, and they are genuinely different. The number of particles in this room, the room you are in, the space around you as you lie here listening, is not a fixed fact about the room. It is a fact about you, about how you are moving, about the path you are following through space-time, and the way that path shapes your experience of the quantum fields that are always there, always fluctuating, in the ground state that we call empty. Empty is not a property of space. It is a relationship between space and the observer who measures it. That is not a metaphor. It is not a poetic flourish wrapped around a piece of ordinary physics. It is the direct, literal, mathematically precise implication of quantum field theory applied to observers in different states of motion. The Unruh effect is the simplest, cleanest, starkest demonstration of it. And it leads somewhere even more profound if you follow it carefully. We tend to think of the physical world as a collection of facts, the number of particles in a box, the temperature of a gas, whether a region of space is empty or occupied. We tend to assume that these facts exist out there, independently of us, waiting to be measured. Measurement reveals the fact. The fact was already there. The Unruh effect says, not always. Some facts, some of the most basic seeming facts, like whether empty space is empty, are not out there, waiting. They depend on the observer. Not because the observer is confused, not because the measurements are inaccurate, but because the universe itself does not assign a single answer to the question. The universe is more generous than that. It gives each observer the answer that belongs to them. And those answers can differ. Physics encountered something like this once before. When Einstein developed special relativity, he showed that the question, how long is this event in time, does not have a single answer. An event that lasts 1 second for one observer lasts a different amount of time for an observer moving relative to the first. The event is the same event, the time is genuinely different. Not because anyone is wrong, but because how long an event lasts depends on your state of motion. The Unruh effect does something similar, but deeper. It is not just the duration of events that depends on your motion. It is whether events are happening at all, whether particles are present, whether the space you inhabit is empty. You are, in a sense, not just measuring the world, you are partly constituting what you find in it, not by an act of mind, not by any mystical influence of consciousness, but by the simple physical fact of how you are moving. The vacuum you encounter is the vacuum of your motion. There is a kind of strange comfort in this too, or at least a kind of rest. We are so accustomed to thinking of the universe as a vast, indifferent thing, full of fixed facts that exist without any reference to us. And in many ways it is. The laws of physics do not bend to our wishes. The speed of light does not adjust to our preferences. The equations do not negotiate. But at this deepest level, in the quantum fields that underlie all of matter and energy and space itself, there is something that is not indifferent to your motion. The vacuum responds to how you move through it, not magically, not by knowing you are there, but by obeying laws that make the experience of emptiness a local, personal thing. Your vacuum is yours. The warmth you would feel, if you could feel it, belongs to your path through space-time. You are lying very still. Your acceleration is 1g, held by the Earth below you. Your Unruh temperature is 4 times 10 to the negative 20 Kelvin. Your vacuum is faintly, unmeasurably, genuinely warm. And somewhere in the great particle accelerators at SLAC in Menlo Park, California, at Fermilab in Batavia, Illinois, and at CERN and its cousins around the world, electrons are whipping around in circles at close to the speed of light, accelerating so violently that their spins may be telling us, in the only language subtle enough to carry the message, that the vacuum around them is not entirely quiet. And in a laboratory at the Technion in Haifa, supersonic flows of ultracold atoms moved through a precisely shaped landscape of laser light, and at the boundary where the flow crossed the phonon sound barrier, pairs of quantum vibrations were born from the vacuum of the condensate, entangled, thermal, the mathematical shadow of Hawking radiation, in the most cold and controlled setting human hands have ever assembled. None of these is the thing itself. None of them is a thermometer rising in empty, accelerating space. But they are fingers pointing at the same moon. And the moon, we are increasingly confident, is there. At some point, perhaps in a decade, perhaps longer, a laser will be bright enough, and the signal will be clean enough. And someone will look at the spectrum of radiation from an electron accelerated in a petawatt pulse and see, beneath the noise, the thermal signature that the Unruh DeWitt model predicts. Or someone will find a more clever analog system, one that maps the vacuum physics even more precisely. Or theorists will find a new window, a new indirect test. In some corner of the theory we have not yet thought to look. And when that happens, when the first genuine empirical shadow of the Unruh effect falls across a detector somewhere, it will be a confirmation of something that was predicted on pure theoretical grounds in 1976. Half a century of trust in the mathematics before the first hint of measurement. That is not unusual in physics. Gravitational waves were predicted by Einstein in 1916. They were detected in 2015, 99 years later. The Higgs boson was predicted in 1964 and found in 2012, 48 years on. Physics has a long history of confident prediction, careful patience, and eventual confirmation. The Unruh effect is following that same quiet arc. We have come a long way tonight. We started with 2 observers and 1 patch of space, and we have ended up, perhaps unexpectedly, with a different way of understanding what a fact is, what a measurement means. What it says about the universe that emptiness can be relative to motion, the same way that time is relative to velocity. The quantum vacuum, that not quite nothing that underlies all of space, that fluctuates and pushes and can be measured by the Casimir force between 2 uncharged plates, that same vacuum is not the same for everyone. The universe is not a stage on which events happen. It is something stranger and more intimate than that. It is a structure that shapes itself differently for each observer passing through it, obeying laws that are universal but yielding experiences that are personal. That is what the Unruh effect is really saying. And it is saying it quietly, in the language of thermometers and Bogoliubov transformations and Rindler horizons, in a voice so soft that we have not yet built the instruments to hear it directly. But we know it is there, sitting in the mathematics, patient and warm and waiting. We started tonight by imagining 2 observers at the same patch of perfect vacuum, one still, one accelerating, one reading nothing, one reading a faint warm glow. And we asked, how can both of them be right? Now you know, the vacuum is real, the fluctuations are real, the fields are always there, but the question of how many particles those fields contain, of whether the space is full or empty, that question does not have a single answer. It has an answer for you, and an answer for them, and those answers are both correct, and they differ. Because you are moving differently through a universe that takes motion seriously at the deepest level it knows how. Empty is not a fact about space. It is a fact about how you move through it. And that, if nothing else from tonight stays with you as you drift, that single idea, turned over slowly in a quiet mind, is one of the genuinely strange things that careful human beings have discovered about the nature of things. Not in philosophy, not in metaphor, in mathematics, in physics, in the equations that have survived every test we have been able to devise. Wherever you are listening from tonight, I hope the strangeness of it has been the right kind of strange. Not unsettling, not anxious, just the quiet, clean disorientation of understanding something that the universe genuinely is, even when it refuses to fit inside the ordinary pictures we carry around of how the world works. The vacuum around you is the lowest energy state of all the quantum fields. It is not empty, but it is as quiet as things get. And in that quietness, in that barely warm hiss that the physics says is there for you and not for an observer falling freely past you, there is something almost like a kind of company. The universe offering its own faint warmth to the specific path you are taking through it. If you enjoyed this slow journey tonight, if this strange corner of physics gave you something to rest inside, a gentle like and a subscription means more than you might think to a small channel like this one. Small creators like me rely on your support to keep these journeys going, and every one of them helps. And if you find yourself willing, tell me in the comments, where in the world are you listening from tonight, and what time is it in your corner of the dark? Sleep well, fellow voyager. The next journey keeps until you wake.